Okay, so hello everyone. My name is Adel. I am a PhD student from Algeria, and today I'll be talking about a little work I've done with my supervisor concerning new methods for building up Ricci-Solitons in Riemannian manifolds. So the plan for my presentation will be divided into 4 parts. We start off with an introduction, then we'll talk about a deformation of matrix, and we introduce our new methods, and then we will conclude our presentation. So the notion of Ricci-Soliton is basically a generalization of Einstein manifolds. It was appeared by Hamilton, and basically a Ricci-Soliton is a fixed point solution for the Ricci flow. Ricci-Solitons have been studied extensively nowadays, and they've been applied basically and a lot in contact geometry, because contact geometry is, like everyone knows, the manifolds are classified into 12 classes, where each class is by certain relation, which really helps in computations. So a Ricci-Soliton is basically a Riemannian manifold associated with a vector field at the constant lambda, which is by the following equation. So we'll talk about, so what have we done? What is the work we've done? So given the Riemannian manifold, we've deformed the initial metric, and we've built a Ricci-Soliton on the deformed metric. So as you can see, the idea here is revolved around the same idea that we contact with contact manifolds, like contact structure. Like we take a vector field, we will call it a characteristic vector field, and we'll build around it our deformation. This is practically a special case of generalized deconformal deformation, where the constant b and a are equal. The constant b is equal to 1. The constant a is equal to square root 2. For the distribution here, the notation is simply kernel of the closed form, which is the covector of the characteristic vector field. So for this particular case, we call this deformation as d-isometric deformation, because the metric is the same on the distribution. So what about the generalized deformation? Well, this deformation has some weaknesses. Basically, often the initial structure is not preserved by this deformation. We've applied complex manifolds, and usually you end up by giving strong conditions functions b and a, but it also has strength, as it's proven. Like I said, I used it in cosymplectic manifold, and given certain values of b, we can prove that any cosymplectic manifold is isomorphic to a sphere, locally isomorphic to a sphere. So after defining our deformation and the new metric tile G, the TÜBİTAK connection, the Riemannian curvature connection, the Ricci operator, and the Ricci-Tensor. And the idea here is to write each and every new tensor with the old one. Like, we don't want to compute the components for the new metric. We want to use the old component. So now that we have established every tool, we will build our Ricci-Soliton. So this is a Ricci-Soliton. A Ricci-Soliton, like I said, is a Riemannian manifold associated with the vector v and the constant lambda that verify this equation. Okay, we said in the other introduction that it is a generalization of Einstein manifold. Well, Einstein manifold are basically where this the lead derivative is vanishing here. It means that v is scaling. If v is scaling, then the structure is Einstein. Now here, what we need to determine, we need to determine the field vector V and the constant lambda. So the idea behind this is to choose a vector V and determine the constant lambda. So a trivial choice of the vector V is to be collinear with the characteristic vector field, So for our first construction, we will consider V is equal to Fz, which is parallel to C. And after direct computations, we obtain our first result. Now notice that if F is constant, then the constant lambda is positive, strictly positive, which means that the soliton is shrinking. Okay. Now to written our claim, we give the following example. So the example is the hyperbolic space product, the real line. Okay, so we give an orthonormal basis of the space, we compute its in metric, we compute the non-vanishing component of the Lévy-Civita connection. We do the same with the curvature tensor and the Ricci operator and the Ricci tensor. And after applying our main result, we get a Ricci. Okay, so the soliton is steady only if A here is equal 0. Otherwise, it depends on the sign of A. If it is positive, then it is shrinking. If are known as real space forms, and its curvature tensor is given by this relation. So using contraction, we can compute each component needed for our work, and we give the following basically as okay. So for our second result is, so in the first result we consider the initial manifold apart from it being a Riemann manifold. For the second result, we will consider having a Ricci-Soliton structure on the initial manifold, and we will deform it. And we've obtained that the initial Ricci is transferred to the deformed structure. And gave this example, the 3D cigar. Well, the 3D cigar is simply a generalization of a cylinder in. It's basically wherever you cut it with a plane, you get a cylinder. So we do the same work we've done in the first example. We give an orthonormal basis of our space, we compute the metric, and we apply our results. Now this, like the results, like it is mentioned in the results, we give the manifold is has a structure, a Ricci-Soliton structure, and we've proved that the deformed manifold, the deformed structure, has the same Ricci-Soliton structure. Okay, and after that we turn our focus to 3D dimensional manifolds. It means that the conformal curvature tensor is vanishing in 3-dimensional light. And using this information, we can conclude with direct computations the following result. And we finish with this example. Now, what can we do next? What's next? Where can we go from here? So we haven't used any special vector fields in our work. We simply suppose that the vector field V is collinear to the characteristic vector field, one can maybe use the fact, other facts such that V is force-forming or torqued or recurrent vector field, concurrent vector field. These vector fields really have rich properties. They can either add properties to the structure or make the structure more rich simply. Okay, in conclusion, so what is next? So we've already applied these methods on almost contact manifold, like post-symplectic manifolds and Kenmutsu manifolds. So in Kenmutsu manifold, the deformation actually destroyed the initial structure. So we've applied this on beta Kenmutsu manifold or F Kenmutsu manifold. And we could apply the same methods introduced here to determine Ricci-Solitons. And lastly, I like to point out that the study of Ricci-Solitons is very important to define singularities, because in mathematics, we don't have a definition of singularity, space of singularities, or what is a singularity. And also Ricci-Solitons are a powerful tool in physics. That's why it has attracted the attention of many mathematicians. Now, why I say this? Because there was an attempt to solve the Navier-Stokes equation using a conformal deformation of a Ricci flow, but they faced the same problem as the analytic way, which is the perturbation. When the perturbation are high, we cannot define the trajectory of the flow. So maybe some people consider that the movement of the fluids, like for example water, is chaotic, but we don't know yet. And that's it. Thank you.
Thank you, Professor Delloum. Is there any question or comments?